This lecture is devoted to the concept of orthogonality and orthogonal complements in an inner product space. Let's first write down the definition of what it means for two vectors to be orthogonal. U and V, two vectors, are orthogonal when the inner product is equal to 0. This is exactly how it worked with the dot product, of course. Two vectors in Rn are orthogonal or perpendicular to each other when their dot product is equal to 0. And now you can just replace dot with your more general inner product, whatever that may be. Just like with vectors in Rn, we write U perp V when we have orthogonal vectors. If U and V are orthogonal, that means in particular that the triangle inequality will give you equality. But what does it mean for two vector spaces to be orthogonal? Let's consider that next. Our definition of orthogonality for vector spaces will be this. Two vector spaces, U and V, are orthogonal to each other if every vector of U and every vector of V are orthogonal to each other pairwise, meaning their inner products are 0. There's a little bit of subtlety to this definition here, so let's take a look at an example. Think of a flagpole coming straight out of the ground. We'll think of that flagpole as being kind of like the z-axis, and we'll think of the ground as being the xy plane. These are both vector subspaces of R3. In this case, we would say that the vector space U, given by the flagpole, and the vector space V, given by the floor, are orthogonal to each other. Any vector that I can find in the floor is perpendicular to any vector that I can find along the flagpole. But what if you think of the floor and the wall of a room at perfect 90-degree angles from each other? Are these vector spaces orthogonal? You may be surprised to find out that no, the wall and the floor are not orthogonal to each other as vector spaces of, in this case, R3. So more precisely, I'm thinking of the floor as being the xy plane, and I'm thinking of the wall as being the yz plane. The reason why these two vector subspaces of R3 are not orthogonal to each other is because this condition that every U and V in them have inner product equal to 0 is not satisfied. And the problem is going to be where these two planes intersect, because they intersect in a line. In the way that I've drawn it, they intersect in the purple line. So if I take a vector here in purple, say maybe this vector lying along the purple line, and pair it with itself, I will end up with the vector V inner product with V. And that is not going to be equal to 0 unless V is the 0 vector itself. So the issue is that it is not true that for every vector U and U and every vector V and V, the inner product of U and V is equal to 0. So even though these planes are at 90 degrees from each other, they're not considered to be orthogonal as vector subspaces of R3. So the definition is a little bit subtle in that way. All right, let's go over some facts about orthogonality. If you have two subspaces, capital U and capital V, that are orthogonal to each other, then their intersection must be the 0 vector. In the previous example, when we looked at the wall and the floor, the intersection was not just the 0 vector, it was a whole line of intersection. And so that meant that these spaces were not orthogonal to each other. If the dimension of U and the dimension of V add up to be greater than the dimension of the entire space, then you automatically know that these vector subspaces cannot be orthogonal because they're necessarily going to have some sort of non-trivial intersection. For the second fact and the third fact, I want to bring to mind two pairs of vector spaces that we already know to be orthogonal. The row space and the null space, or orthogonal complements in Rn. The column space and the left null space are orthogonal complements in Rm. And next we're going to look at an explicit example of this. We now have a well-established procedure for calculating the bases of the row space, the column space, and the two null spaces. So what we'll do in the example is write down those bases, but then observe that these really are orthogonal to each other. Meaning you could pair a vector from the row space and the null space and it's going to be 0. You can pair a vector from the column space and the left null space, and it's going to be 0. So let's take the matrix 1, 2, 3, 2, 4, 6. This is just a simple little matrix. One row operation minus 2 row 1 plus row 2 is going to turn it into 1, 2, 3. I've also worked out the transpose here and then already applied 2 row operations to put the transpose into reduced row echelon form as well. That way we can easily jot down bases for all of the 4 fundamental subspaces. So jotting down those bases, we find that the row space has one vector in its basis, and it's given by the row vector 1, 2, 3. There is one independent column the first column. And so the column space is going to consist of the first column of A as its basis. The null space is going to have two vectors in it, and then the left null space will have one vector in it. And you get the bases for the null space and the left null space by investigating the dependencies of the columns in the matrix A and in the matrix A transpose. And that'll give you these four fundamental subspaces written out. So what I want to observe in this little example is first that the vectors in the row space are orthogonal to the vectors in the null space. Let's just calculate that directly. We have only one vector in the basis for the row space, and anything else in the row space is going to be a linear combination of that, so a multiple of that. So we can just check it on the basis elements. So if we take 1, 2, 3, and we pair it with the dot product with any of the basis vectors of the null space, like minus 2, 1, 0, we're going to get 0. And indeed we do. We get minus 2 plus 2 plus 0 equal to 0. Likewise, 1, 2, 3 dot product with minus 3, 0, 1 will give us minus 3 plus 0 plus 3, and that again is 0. We will also get a dot product if we take anything else in the row space dotted with anything else from the null space by linearity. Let's do another calculation to check that vectors in the column space are orthogonal to vectors in the left null space. So now we're going to take our basis vector from the column space, 1, 2, and pair it with our one and only basis vector from the left null space, minus 2, 1, and indeed, we get 0 from that dot product. This is a simple example, but we can see that these are orthogonal complements from each other very easily. And in particular, the only vector that the row space and the null space, or the column space and the left null space, share in common is the 0 vector. I've been using the phrase orthogonal complement, but I haven't defined it really. So let's go over that. Let's assume now we're working in Rn, and U and V are vector subspaces of Rn. We saw the definition of orthogonality for subspaces, and it meant that the inner product was 0 for all of the U and U and all of the V and V. Here, the inner product is just the dot product. Well, let's now just take one subspace of Rn, U. If you have a subspace of Rn, then its orthogonal complement is the set of all the other vectors in Rn such that those vectors V dot with U in U and give 0. So it's the set of all the other vectors that are orthogonal to all of the vectors in U. By definition, then, the orthogonal complement of U is orthogonal to U. Another thing that you get out of orthogonal complements is the notion of a direct sum. So if you have your two vector subspaces in Rn, then what we want to know is whether we can describe everything in Rn uniquely as something from U and something from V, which is kind of like asking whether U and V overlap at all. And what we saw before was that if U was orthogonal to V, then their intersection would be only the trivial vector. So the statement here is that if each vector x in Rn can be written uniquely as something from U plus something from V, and this is vector addition, then Rn is the direct sum of U and V. And we write Rn as U sum V in this manner. Let's look at a couple of examples. The first example is one we saw before, the floor and the flagpole. More precisely, let U be the xy plane in R3 and let V be the z-axis. R3 is the direct sum of U and V are orthogonal complements. Any vector in R3 is obviously written with 3 coordinates, x, y, and z. The basis for U and the basis for V together will form a basis for R3. Another example is something we saw a moment ago. Given a matrix A, the row space and the null space are orthogonal complements in Rn. The column space and the left null space are orthogonal complements in Rn. As a third example, let's consider the line y equals 1/5 x in R2. Now you can plot this line and you can observe that the line y equals minus 5x is its orthogonal complement because you have two lines in R2 crossing through the origin and they are at 90-degree angles from each other. But let's look at the same thing using matrices. So our line y equals 1/5 x, if we encode this as a matrix, is going to give us 1/5 minus 1, which by applying the row operation 5 row 1, is the same thing as the matrix 1 minus 5. Using this, it's easy to see that the row space is the span of the vector 1 minus 5, which is this line in R2 that we've indicated with green. And the null space is the span of the single column vector 5, 1, which is the perpendicular line that we've indicated in purple, also drawn in R2. These are orthogonal complements of each other, and clearly they intersect only in the 0 vector, which we're seeing here as the point 0, 0, the origin in R2. So to summarize, let's look at a couple properties of orthogonal complements. Let V be any vector subspace of Rn. The dimension of V plus the dimension of its orthogonal complement has to add up to the dimension of the total space, N. V and its orthogonal complement are direct summands that add up to Rn. Rn is a direct sum of V and its orthogonal complement. And also, if you take the orthogonal complement of the orthogonal complement, you get back to V. And because it is worth repeating, let us consider yet one more time the 4 fundamental subspaces of a matrix. The row space and the null space are orthogonal subspaces of Rm. And therefore, Rm can be written as a direct sum of these two. The row space of A transpose, also known as the column space, and the left null space are orthogonal subspaces of Rn. Therefore, these two are the direct summands of Rn.